Welcome, everybody. We are back with season 2, episode 1 of the Quantum Analyst Roundtable. I am joined, at least in spirit, by Shahin Khan. He'll be back next time. But here in spirit and physically, digitally, Doug Finke, David Shaw, James Sanders. How are you all doing, my friends?
Doing good.
Good at this end.
Very well.
Some of the most famous are 3 other very famous names in quantum: Alain Aspect, John Clauser, and Anton Zeilinger. I think much has been written and said about them. We'll add our congratulations. Pretty big deal, no?
Yeah, I think it's a great event for the field. There was just one touch of sorrow for me. It reminds us that John Bell has left us, because obviously I think everyone believes he would have been on those list as well if he was still alive. He obviously had a great seminal contribution to the field, but it's great to see those other guys recognized.
It also leads to a lot more questions from friends and strangers. Don't you work into this quantum thing? Can you explain to me what the Nobel Prize was for? So that's been a fun little added side benefit of that Nobel Prize, which is not an official Nobel Prize, by the way. It's been added by the Swedish Academy as an additional prize. It is not part of the founding prizes of the Academy, but recognized as such.
Yeah, I think also there's one other benefit, that it really gives a message to the world that this quantum stuff is real, that it's not just some pipe dream that physicists are pursuing, and it just adds to the credibility of the industry.
A lot more credibility in the industry was evident since our last episode, and as recently as this morning. You might have seen the press release or the news. A little company out of Boulder, Colorado, raised just a modest little amount, 110 millions in a B round, and bringing onto their board an old friend of mine from Chicago, Chris Galvin. I remember I was pitching Chris small little quantum startups 4 years ago, and he always said, yeah, that is a little too risky. So Cold Quanta, a big check and not risky, and very exciting show of credibility.
Yeah, I've always really liked the Cold Quanta story. I mean, obviously some of the headlines go around the option to build a neutral atom quantum computer, and I think these devices have got a real unique opportunity to look at analog quantum simulation in the relatively near-term period. But I think one of the other great things about Cold Quanta is it's got such strong story about other product areas that it can get involved in. It's got a very strong tradition of selling cold atom systems for sensing applications, potentially networking applications. Notable, it's already got space qualified equipment up in the International Space Station. I think it's a great diverse opportunity of revenue stream. Great example of how you can have a wide presence in quantum tech.
And one of the earliest, and I believe biggest vendors of atomic clocks as well, quantum atomic clocks. The press release also mentioned a reference by a consulting company on how the quantum computing market will reach 850 billion very, very soon. So we're excited to hear that as well. PsiQuantum, and Doug, you reminded me of that. Do you want to talk about their 22.5 million, not funding round, but it's a contract with the Air Force?
Yeah, actually, there are 2 deals that happened, let's say, in the past few weeks, where various government-related research agencies have given some contracts. The first was PsiQuantum is making a deal, $22.5 million with the Air Force Research Lab. I think a lot of this has to do with some push from Senator Schumer of New York, who's helped free up some of that funding. But I would also point out that the German Aerospace Center, it's called DLR. DLR is the initials in German. Has just issued, if I remember correctly, 500 contracts for about $200 million for ion trap computers. And I think there's 4 or 5 different European companies that are all related, working in that area. And it has a goal of building a 50 qubit machine and then a goal of networking those machines, and there are different people working on different pieces. So Germany could be definitely a big player in future ion trap machines.
Very interesting to see Universal Quantum on that list of German contracts, leading one of the consortia, I believe. I mean, it's a business I've always thought it really stood out as having, always stands out as a business of having a de-risked long-term roadmap for how you put a machine at scale together. And it is interesting to see the UK has been a bit of a hiatus as it waits to get its phase 3 strategy through the government. It's interesting to see Universal Quantum going to Germany to top up its funding.
And this funding by the DLR, the Deutsches Zentrum für Luft- und Raumfahrt, is part of the overall German package. So this is just the allocation of those previously committed funds and a consortium approach. They're very good at coming up with short little names and abbreviations for these programs, but putting together semiconductor companies, optical companies, but then be it Universal Quantum in one of these 3 projects, Parity Quantum in a second one, and Kudor in the 3rd project that will be splitting these over 200 million euros and dollars. We have another funding round, a little different, but sticking to Europe, and I know that Doug wants to make a comment about that. But Quantrol OX got a 10.5 million award by the European Innovation Council, and that comes in few different phases to help Quantrol OX develop their machine learning based control software. So, you know, part of the control stack in quantum, and another European company with a significant seed early stage kind of funding.
Yeah, I think that's an area that just the whole area of control software, control firmware is not probably as well known as perhaps some of the people working on the chips. But it's very important. The fact that by controlling the pulses, either the microwave pulses or the lasers or whatever, you can have a significant impact on the qubit quality. So there are a number of companies in that area. There's Q Control. There's Benchmark, which was acquired by
Machines.
Right? And now Control X. So it's an area to watch, and certainly an area I think that anyone developing a quantum computer should pay attention to, because again, I think it can make a big impact on your qubit quality.
One thing that I wanted to add on to Doug's comments, and I think I spend a little more time dealing with classical systems than anyone else, except maybe Shahin on the podcast, but he's not in today, so I guess I'll be the one to voice this. I think in the past 18 months, there's been a pretty big swing toward the idea of, sovereign cloud, sovereign systems, both for enterprise compute and more HPC. And that trend is kind of inevitably coming to quantum computing, especially when we start seeing moves, especially with the US government attempting to regulate the export of systems that would be useful in building a quantum computer to China. I suspect that there is a little bit of higher appetite for independence among not just European countries, but European companies to stand up an independent supply chain for all of the components that would go into a quantum computer, not just control, not just QPU, because of geopolitical concerns.
And you just handed me the buzzword that I wanted to pick up on. Doug, you had mentioned that earlier when we spoke. People always talk about the quantum war between the US and China, but is China the wrong focus here? We just saw 250 million USD spent in Europe.
Yeah, I don't think we can ignore China, but I just think that Europe is very strong also. And I'll include the UK as part of Europe in this case. Lot of activity there, a lot of good technology, and you read the country plans of many of these countries, and they want to be the dominant leader in quantum technology. They don't want to cede everything again to Silicon Valley. They think that this is their opportunity to, let's say, equal the stakes or equal the leadership. The U.S. has led in things like semiconductors, the early computers, and social media, but now a lot of these countries see that quantum is their opportunity to catch up. And by the way, I will also give honorable mention to Canada as well as Australia. They also have some great companies in those and research in those areas. They just aren't quite as big. They don't have as many people. So I don't think that Canada and Australia will dominate quantum computing, but they'll definitely be important players.
I always love speaking with you guys from the US because I think it's just really quaint that you assume the US is leading in quantum computing. It's just touching.
So who is leading?
Well, to be honest, I think one of the things that we all need to be more cognizant of is that some of the businesses that have been able to surge ahead and get headlines, that's not the same thing as do we believe they've got scalable architectures for the long term. And I think you really have to look around. There's a lot of interesting ideas as you look at those countries that Doug's just been listing off. There's a lot of interesting ideas for how you can put together architectures that they're maybe not as advanced in this first demonstrate me a qubit step, but have they got a better scaling profile to get to large scale fault tolerant quantum computers? Well, they've got an argument there, a lot of them.
Go Europe. Moving away from funding news, but sticking to the larger quantum tech ecosystem, the eponymous founder of Rigetti Computing Inc., and Rigetti, one of the most famous, oldest, being founded in 2013, and largest with just short of 200 employees, I believe, startups in the space, is stepping down as CEO to, as the announcement says, focus on advancing its products and technology. Much of which he invented and drove. The stock price went up 4.5% on that news. I'm not sure if that means anything. Is that a good news or bad news?
Well, that type of step is very common. We see it all the time in the classical industry. There's some technically focused founder who starts the company and brings it to a certain level. And then the board of directors and the management, decide that the company has grown so much that they need to start thinking about how do they want to reorganize things. And it's good that Chad will stay around and guide the development because they've done a lot of great things. But at the same time, I think a lot's going to depend on who they come as the new CEO. I saw that a search is in place. We'll just have to see if they get the right person to take his place.
And Rigetti is slated to release their financial results in just short of 2 weeks, as is IonQ and a couple other companies. So we'll gain some interesting insights there and how these companies have actually been able to progress. Any other observations before we look at some more tech-driven developments? James, I see you.
Sure. When you look at the stock prices for the 3 or 4 publicly traded quantum startups, you can see that and see what their highs for the year or year to date are, and feel a little glum about it, frankly. And that's just a reflection of the broader market. At the same time, there are scalability challenges, as David said, and it will be interesting to see how these things develop and how, in some ways, I do kind of suspect that the noisier people in the room also have the noisier qubits in the room, and some of the things that haven't been as well publicized might actually be the route to a scalable quantum computer. But that's more of a personality observation than a technology observation.
And a lot of these stocks are still very illiquid. So while many of them are 40, 50, 60% down, that has to be taken with a grain of salt, as these are not yet very efficient markets in the economical sense of probably reflecting the true valuation or performance of these companies. So let's look at some product and tech news, and let's stick to computing. Our friends at Quare Computing are making a big announcement. Doug, I think you have some insights on that.
Yeah, so Quera is a Boston-based startup working with some research, I think originally from Harvard, and they are another neutral atom company. So you just talked about cold quanta. They have developed a 256 qubit analog quantum processor. And as of maybe an hour ago, a couple hours ago, it is now available on Amazon Web Services. So I've looked at the details a little bit. It's still new. Programming it is their own software called Blockade, which is programmed in Julia. So it's maybe an issue for people to use it, but they wanted to get it out there to have end users try it out and see it. Certainly in terms of scale, it's the largest we have out there. But again, it's analog. It's not gate based. There are some advantages with analog quantum computing. Some people believe that when you talk about quantum advantage, that the analog quantum computers may actually be able to achieve quantum advantage before the fully gate-based approaches, but we'll have to see. So another player, another machine hooked up to Amazon Web Services. I think that's like the fifth machine that Amazon Web Services is now hosting, and we'll see what happens.
It might also be interesting to point out that while this is coming online, the D-Wave quantum annealer has been removed from the AWS bracket service and has moved to the AWS marketplace.
Yeah, I think that the issue there is I think they wanted to offer Leap. I'm not sure Leap was fully available on the bracket service, and it's a way of doing it. Perhaps it might expose the machine to more customers. I mean, if you're using D-Wave and you're already a customer, already going through AWS, I'm not sure it's a big deal.
One thing I just want to go back to the Quera announcement again. I think it's very interesting, the analog aspect that Doug's referring to, very interesting. One of the things I've often been a bit nitpicking in the past about how active some of these neutral atom machines have been in describing their onward path of, can they implement a gate model, can they implement error correction, and I think one of the credits of Quera and strength of its academic founding team is they have put out a number of papers that are seeking to detail that roadmap as how you can move a gate model approach forward in their architecture, how you can create errors. I think we are still at an earlier stage, but they're clearly up for wanting to tell that story. How robustly they can tell it remains to be seen.
Beyond the world of quantum computing, quantum networking and quantum encryption, and many of us just returned from the IQT Fall Conference in New York, which made this their main topic, continues to expand. And an important announcement here was made by Aliro, the world's first full-stack entanglement-based quantum network solution. And this is a big lift. They call it AliroNet. It has quantum computing capabilities on the emulation side. It has a quantum internet. It has distributed quantum sensing capabilities, and then of course the quantum secure communication channels. All of this delivered in 3 different modes: an emulation mode to design and kind of build your applications, a pilot mode where you can do these trial and error applications, and then a full-scale deployment mode, and all of that on their own proprietary software stack, Aliro Orchestrator, which has not only the emulator and simulator, but also the operating system and the control systems to run all of this. So how should we put this kind of announcement in context? It sounds rather overwhelming.
I think it's really interesting. Congratulations to Alira for getting out in front of this. It seems on the one hand you can make this seem like this is a way ahead of its time. You know, people don't. We've not really got all the components to build a network like this yet. So why do we need a whole software platform helping us do that? But I hark back to you know, in a company strategy sense, look at the success that the IBM quantum network was. They started putting these machines on the cloud. Really, there was no real reason to put a 5-qubit quantum device on the cloud because you could simulate it. But they developed a whole momentum in the community, a momentum for their model of how things should be put together. And it could be that we see an opportunity for someone to grab that momentum in this space, the entanglement networking space, and that's what Alira might be on to here. I did enjoy teasing them a little bit though in NYC, because obviously in the US, you know, quantum key distribution is prohibited by the authorities. But out here in the rest of the free world, you know, in Asia and in Europe, QKD is allowed, and it's notable that, you know, the companies in the US, whether it's Alira, whether it's Qubitekk, they're deliberately dropping QKD from their marketing material. Obviously, in fairness, what they're doing is a much more advanced version of it's not basic prepare and measure QKD, it's an enhanced entanglement QKD. But it is funny to watch how the marketing contortions try to spin to the local audience.
Hey, David, I need to perhaps correct you. I would not say that QKD is prohibited. I would just say it's not recommended at this point by some of the government agencies, and there are certainly people working on it diligently. One thing to point out about Alira is that they're not a hardware company. You know, they have software and system integration expertise. They are buying their components from companies like Qubitekk and others to help do this and help set this up. And one of their services is if you're a customer and you want to set up a network, they'll give you a recommendation about which hardware components to purchase. I would also mention another thing that came out at the IQT conference very, very quietly, but Zapata is now getting into I'll call it the networking services business. It's much different than their quantum computing software. They will help customers do assessments and testing and verification, and they're just rolling out right now, you know, some services that will help customers do that. So that will be another revenue stream for them. I don't think they will actually be implementing and being, you know, updating code on people's servers themselves. They will partner with consultants and other companies that are more attuned to doing that type of thing, but they are branching out.
In terms of quantum internet, I will dust off the maybe slightly overused historical example of when you look at the foundations of the internet and ARPANET that preceded it, that development of that started in the late 60s and early 70s. And computers at the time, classical computers at the time, were not particularly advanced in the same way that, I mean, relatively quantum computers now are not particularly advanced. So it is time to start building the foundations for a quantum internet, despite how, you know, maybe propeller hatty of an idea this seems to be to people.
I've got to add, obviously, a big plug for Europe. I mean, you can't talk about this and not flag what QTech have done. QTech and their involvement in the Quantum Internet Alliance in the EU has been, you know, instrumental in getting momentum around this in the wider field, I believe, and I think the work they're doing is great.
And another offering that made some waves at IQT, and I remember you, David, commenting on that, was Toshiba. Can you briefly talk about that?
It was one of the highlight, well, probably the highlight of the NYC show for me. It wasn't a surprise there to hear, you know, the Toshiba CEO talking about their QKD system, which is a leading you know, has leading performance stats in the conventional QKD market. Not a surprise there. They've been very active. Not a surprise that he talks about their digital annealer that's obviously made great strides with quantum-inspired algorithms. But what was really eye-opening was he came in with this the announcement that they have this new gate model superconducting circuit qubit technology lined up, which they're called double transmon. I think a lot of people observing the field will have seen, that all of the top companies in superconducting circuits are talking about tunable couplers now as a way of suppressing crosstalk. And effectively what Toshiba's double transmon architecture is a souped up, double removed tunable coupler. And the simulations they've done on it, because this is not real hardware, it's a simulation of what they think the performance is. They're talking about very high, 4 nines performance stats is what they claim from the simulation, very fast gate speeds. And I was so impressed by someone, but the CEO to come on and not give the normal, if you like, general warm flannel around these subjects, but to come in and address a spot-on topic at the heart of it. How are we going to deliver enhanced fidelity in superconducting circuits? No doubt they've patented this thing, and no doubt we'll see its hardware stats come out in due course when they physically demonstrate it. If it can do what they say it can do, it's very big news indeed.
Good. Let's wrap up with some more quantum computing thoughts, and specifically 3 papers that all talk about the same thing. When will quantum computers finally be able to do something useful, but from different angles? One is the IBM roadmap and how IBM is 100% confident in their ability to deliver quantum advantage. Another one talks about error correction and quantum volume. And the third paper specifically looking at the quantum advantage in chemistry and asking the questions if maybe we've already delivered it, but not really noticed it. If you look at the IBM paper, and I was fortunate enough last week to be invited to the IBM Watson Research Facility in Yorktown, so we actually were able to see 16 or so of their quantum computers and in 2 different small little labs, or rather large labs. We were able to see some of the new technologies they are working on. We're able to see the IBM One system that really does look like the future. But IBM's roadmap, and they shared a lot of detail around that up in Yorktown during the full day, really consists of 4 main points in terms of achieving quantum advantage. First is to focus on a problem that admittedly will offer a super polynomial quantum speed up and advancing your theory and your algorithms towards that goal. Secondly, the use of error mitigation tools to get more sophisticated controls at that level. Third, improvements in the hardware, of course, and the big milestone here for IBM is 4 nines on the QPU fidelity levels. And fourth, a modular architecture that really starts to link some of this higher performing hardware. And they detailed this in a 20-page paper by Jake Gambetta and his team with a timeline that is pretty aggressive. Your thoughts on that?
When I talk to people in the quantum industry, there's a definite divide between people who say that we will need a fully fault-tolerant machine before we achieve quantum advantage. And there are others who think that with NISQ, we'll be able to do that. IBM is definitely in the latter camp. They are doing a lot of different things and pursuing various types of hybrid quantum computing, mid-circuit measurement, and circuit knitting, all sorts of techniques. They've been really studying this because they have a very strong belief that some of their upcoming machines, and maybe the several hundred or a few thousand qubits, will be able to deliver quantum advantage. So they're definitely doing that, and we'll see if they're correct, and the other people who believe you need fault tolerant are wrong.
Yeah, I think Doug's put his finger on the first big headline point of the paper, that they've come out so strongly on that. We do believe we can do it with NISQ. But there was another aspect of the paper that really grabbed my attention. So many so many existing architectures, leading players have been banking on the 2D surface code as their error correction approach for them to have a roadmap to fault tolerance. Very notably Google and its approach, but so many quantum computing startup decks, you read it and they'll mention the 2D surface code as their way of delivering fault tolerance. And one of the really striking things about the IBM paper is that really argues that the 2D surface code isn't going to be good enough, because it's pointing out that the overhead are just very onerous with the fidelities that people are, realistically being able to reach across the different operations required. And they strongly argue that the way forward is higher connectivity, what are called higher connectivity quantum LDCP codes. So it's a general, a 2D surface code is a type of LDPC code. It's a concept that comes from conventional coding theory. But if you allow yourself to have a higher connectivity, not just a 2D nearest neighbor, and a lot of people want to use 2D nearest neighbor because it's relatively easy to aim a device that can deliver that. But if you can go beyond that, then you've got access to a much more efficient ratio between physical and logical qubits, potentially better single shot error correction and decoding techniques. It could be a much more efficient architecture, and it's very interesting. It's very interesting to see a big player like IBM out there saying we really need to push on beyond the 2D surface code.
The second paper looking at the quantum volume and asking the question of how valuable really NISQ error machines are. And I didn't read the entire paper, so those of you who did, back me up. But a lot of interesting findings here too, and maybe they can be summarized as follows, saying that general QV is a good benchmark. It lacks an accurate representation of backend fidelity performance. It also drifts over time, so not for yet and not perfect yet in terms as a benchmark. CLOPS, the new or improved approach by IBM of measuring performance, is singled out as a methodology that might be able to address that. And interestingly, and not surprisingly, the Quantinuum H12 machine is being singled out as well for having, by a wide margin, the lowest overall error rate across all of the backends tested, and the highest quantum volume. So not entirely conclusive as far as I understand this paper. Validation of some performance impressions that I think we all know already, and encouraging signs of how to measure performance going forward. Any additional thoughts? Is that a fair summary?
Well,
it's always good. Please go ahead.
I believe this was the Oak Ridge paper, and I think there's a very interesting conclusion that we should also point out. All the vendors, or a few of the vendors, are publicizing quantum volume. IBM, Continuum, and they have new records. And Oak Ridge tried to replicate it, and they were not able to achieve the same numbers that the vendors had. So, it's clear that when people publish these quantum volume numbers, they probably have a team of PhD engineers who are fine-tuning everything to get the best possible performance out of it. But I think the point for the industry is we have to improve things and automate things so that normal people can get those same results. And I think it can happen, but I think you're going to need some more sophistication in terms, again, the control circuits and AI, and how do you do that so people can achieve those same results?
I agree. I think independent benchmarking is a an honest tonic to show us what's really going on with these devices. You've summarized the backdrop already, but one of the things that really jumps out, when I look at the that list of the processors, the list of the benchmarks, the fidelity is actually on offer from these current day devices. Really, they're shockingly bad. These fidelities are not good enough. We have to have devices that can demonstrate they've got a roadmap to better fidelities. The continuum device stands out, and that's great, and hats off to those guys. But even that, it doesn't really have fidelity which is good enough to take it on to NISC applications or fault-tolerant quantum computing. And these guys, we need to be asking them, show me on your roadmap, where is it, how are you improving fidelity?
I think it's probably fair to say that quantum benchmarking is as much a advertising and political statement as it is a statement of a scientific finding. And when you get into politics, when you get into statistics in politics, I guess, what you have are lies, damned lies, and statistics, right? So having the independent benchmarks is always going to be a good thing, as David has said. The downside is actually getting consensus for all of these things. And it is going to come down to, I'm sorry to echo what David just said, but where on your roadmap are you going to achieve these results? And is there always going to be, some amount of embellishment in what you can actually do with these? Probably, but the same is true for classical systems. So these are the same problems that we've seen for decades. It's just now in quantum flavor.
Quantum flavor, and another team looked at a very specific type of flavor, notably quantum chemistry, which is often being touted as probably the most near-term application of quantum computing, and the potential of delivering a speed up or a quantum advantage there. And the paper in question specifically tackled the task of ground state determination in chemistry for exponential quantum advantage, and it didn't find it.
Yeah, this is a really arresting paper that I think is going to be much talked about, and the field is going to have to adjust its rhetoric around, to be honest, because this is a lot of people will say, and I've certainly been in that camp, that the killer app for quantum computing is quantum chemistry and material science. And colloquially, I think we've often got used to saying it's because there's a proven exponential quantum advantage for those applications. And really, this paper takes that argument on and asks us to be much more careful in our language. This paper is a star-studded cast of authors. Is there evidence for exponential quantum advantage in quantum chemistry? And you have from a whole series of different companies, leaders in the field, really examining leaders both in quantum information science, but also in advanced, conventional quantum chemistry, examining really what is the evidence for that. And just maybe to back up a moment and introduce us to that, when we explain the power of quantum computing to people, we're often want to point out and say, hey, look, even to represent the ground state of a molecule, it's an exponentially complicated task to even write that down for a conventional computer. In slightly more technical language, what we're saying is, if I try to do a brute force solution of the Hamiltonian, the basic equation of that system, if I try to brute force solve it on a conventional computer, I can't even write the question down. But the issue is, and the paper takes us through this, that the conventional quantum chemist guys, they've realized this for years. So that's not the way they've tried to solve these problems. They've come up with other approaches. And the paper really asks, well, look, why do we think these other approaches in conventional quantum chemistry, why do we think they scale so badly? And they don't scale that badly because they've been designed not to scale that badly. So really the question is, how close can I get within a particular error of accuracy? So it's a much more subtle question. And equally, you've then got to say, what evidence have I got that my quantum algorithm offers an exponential advantage? I know quantum phase estimation narrowly is great at its own thing, but to actually apply that to quantum chemistry, that there are some other steps. I have to have an initial state. How easy is it to form that initial step? And this analysis really takes us through saying we don't have concrete evidence that this leads to necessarily an exponential advantage. And so the authors are are asking us to be much more prudent in our language around how we assert this. Equally, and I think it's important then to reflect back, I still believe quantum chemistry and material science is going to be a profound application for quantum computers because they are naturally suited to the problem. But it may be that we have to be much cleverer in finding out exactly how they can accelerate and extend what good classical techniques can already do.
And the authors are very prudent in noting that this has no predictive value on improvements in algorithms, on other aspects of chemistry that go beyond the ground state. It's this very specific challenge that they looked at, and nothing else, but sobering nonetheless.
Well, I would just add one comment. I was recently talking with someone from a quantum company. We're talking about competition, but I made the comment that at the end of the day, the real competitor are the classical algorithms, because they are not standing still. A lot of very smart people are continuing to improve classical technology, both in the hardware and the software. And you hear people say Moore's law is dead, that classical computers aren't speeding up anymore. If you look at the total infrastructure, including the architectures and the software algorithms, there's lots of improvement. So that's where the quantum people, when they look at quantum algorithms and quantum advantage, they have to take that into account, make sure that they're not only going to do better than where the classical algorithms are today, but they have to do better where the classical algorithms are going to be in the future.
Season 2 is back with a statement of superposition. Quantum computing, as well as quantum communications, encryption, sensing, are making massive progress in terms of their products and roadmaps, and really getting more and more detailed on how vendors credibly believe they can get there. At the same time, quantum is still a tiny little industry, and we're at the very, very beginning. I think that if you get into it even in a couple of years, you will still be part of the very beginning and the original group of folks in quantum. A lot of challenges remain, and we will continue to analyze them. Thank you so much, David, Doug, James. Shahin will be back next month. I was about to say week, because it seems that we should be doing this more often. The news is picking up as well, and many announcements are slated for the remainder of this year. We will be there to debate, discuss, dissect them with you. Round and round we go. This concludes the Analyst Roundtable.